Namaste dosto. Imagine you're looking at a beautiful round clock. The tiny part of its edge between two numbers is actually an arc, just part of the circle's circumference. Now, if you pick any 2 points on the edge of this clock, say points A and B, and then join them to some other point P, either on the edge or even at the center, you'll notice an angle popping up. This angle is what we call the angle subtended by the arc between A and B. So what exactly is this angle subtended by an arc? Well, start with arc AB, just a piece of the circle's outline. When you connect points A and B to another point, like the center O or a point P somewhere on the circle's edge, the lines you draw meet, making an angle. This angle is formed at that point, and it's the angle subtended by the arc AB. One important thing, the angle subtended at the center is not the same as the one made at other points on the circle. For example, if you look at the angle at the center, angle AOB, it's usually larger compared to angle APB, which is formed at a point P on the circumference. So, picture a circle with its center O, mark points A and B on the circle's edge. They join to form an arc AB. Now, join these points A and B to O, and you get the central angle, angle AOB. Also, pick a point P on the circle and join it to A and B. This forms a smaller angle APB. Both these angles come from the same arc, but they're different depending on where you're measuring from. Let's now zoom in on the angle subtended right at the center of the circle. This special angle is called the central angle, and it plays a big role in the rules of circle geometry. Think of the arc AB again. When it creates an angle theta, that's the Greek letter theta, at the center O, this angle theta directly relates to how long the arc itself is. Imagine you have a radius r, the distance from center O to the circle's edge. Then, the length of arc AB, let's call it L, is calculated by a simple and beautiful formula. Arc length L equals radius r times angle theta. In words, that's L equals r times theta. And here's the catch, theta must be in radians, not degrees. So if theta is in radians, multiplying it by r gives the exact length of the arc AB. Also, a cool fact to remember, among all points inside the circle, the largest angle the arc AB can make is right at the center O. So, angle AOB is the biggest angle you can get from arc AB inside the circle. Visualize a circle with center O and radius r. The arc AB at the edge subtends angle theta at O. This angle theta then tells you exactly how big that arc is. Pretty neat, isn't it? Now, let's move to the angle subtended at the circumference, the edge of the circle, which we call an inscribed angle. Imagine points A and B again at the edge, forming arc AB. Now, pick another point P anywhere else on the circle's edge, except between A and B. If you join A and B to P, the lines create angle APB. This angle is called an inscribed angle because its vertex P lies on the circle itself. Here comes a beautiful relation. For the same arc AB, the angle at the center, angle AOB, is always twice the angle at the circumference, angle APB. In formula words, angle AOB equals 2 times angle APB. This means if you know one of these angles, you can find the other pretty handy, right? Plus, all angles subtended by the same arc at various points on the circle's circumference are equal. So, no matter where you pick P on the circumference, as long as it's in the same arc segment, the angle APB stays the same. Picture a circle where arc AB subtends angles at O and P, with angle AOB and angle APB labeled. Clearly see how the central angle is twice the circumference angle. This is one of those magic properties that make circle geometry both fun and powerful. Can you guess what might happen if P moves around the circle but stays on the same arc? Just remember, the angle stays constant. Now comes the proof. Don't worry, it's simpler than it sounds, and it's very satisfying once you get it. We start with the arc AB, which subtends angle AOB at the center O and angle APB at a point P on the circle's edge. The question, can we prove that angle AOB is exactly twice angle APB? To do this, we use the properties of isosceles triangles. Why isosceles? Because distances OA, OB, and OP are all equal to the radius r, so triangles OAP and OBP each have two equal sides. That's the key. Using these triangles, along with angle addition rules or the alternate segment theorem, we show step by step that angle AOB equals 2 times angle APB. This connection is not just a coincidence. It follows from the equality of sides and a sum of angles in triangles. This theorem is a cornerstone in geometry, used in many circle-related problems and proofs. Once you understand it, solving those questions becomes much easier. Imagine the same circle now, but with triangles OAP and OBP highlighted. Angles inside these triangles add up neatly to prove the double relationship between angles at the center and circumference. Let's explore another fascinating result that follows from our angle subtension discussions. All angles in the same segment of a circle are equal. Picture points A and B on the circle's edge. And now to different points P and Q on the same side of the chord. If you draw angles APB and AQB, both these angles are subtended by the same arc. The theorem states that these two angles, angle APB and angle AQB, are equal, no matter where P and Q lie in that particular segment of the circle. This is called the angle in the same segment theorem. This property is super useful when working on cyclic quadrilaterals or triangles inscribed in circles because it tells us the angles stay constant within that segment, providing powerful clues to solve geometry problems. Visualize a circle with arc AB and points P and Q somewhere on the same segment of AB. You see angles APB and AQB clearly marked equal. A perfect example of this theorem in action. Now, let's put our knowledge to work with a simple solved example. Given arc of a circle with center O and a point P on the circumference such that angle APB equals 30 degrees. Question: what is angle AOB, the central angle subtended by arc AB? Using the formula we learned, angle AOB equals 2 times angle APB. So, if angle APB is 30 degrees, then angle AOB is 2 times 30 degrees, which is 60 degrees. In math words, angle AOB equals 2 times 30 degrees equals 60 degrees. So, central angle AOB is 60 degrees when the arc subtends 30 degrees at the circumference point P, simple and perfect. Picture the circle with these points and angles marked. It makes the relationship crystal clear. Try solving similar questions yourself to get more confident. Time to wrap up. Let's summarize the key points from today's lesson on angles subtended by an arc of a circle. First, remember the main formula. Angle AOB equals 2 times angle APB. The angle at the center is double the one at the circumference for the same arc. Second, the arc length L equals radius r times theta, where theta is in radians. Third, all angles subtended by the same arc at points on the same segment of the circle are equal. So, angle APB equals angle AQB, for example. Remember, an arc can form different angles depending on where the vertex lies, center versus circumference. The central angle is always the largest for a given arc. Also, these properties are beautifully derived using triangle congruence and geometric rules, helping us solve many problems involving circles and cyclic shapes. Before we finish, here's a quick quiz for you. If angle APB is 45 degrees, what is angle AOB? Shabash. The answer is 90 degrees, of course. Keep practicing these relationships and you'll see how useful they are in exams and real-life problems like designing wheels or cricket ground boundaries. Arey wah! Well done today. You're one step closer to becoming a geometry star. Keep exploring those circles,